This video will show you how to get started with analyzing the deformation of solids, and in particular we'll look at elastic deformation. So we saw in class the governing equation for elastic deformation. It's based on conservation of momentum. In order to solve that equation, we need to specify boundary conditions. And there are two types of boundary conditions that we'll use in general. One is based on the displacement and one is on the stress. So the simplest kind of displacement boundary condition is where the displacement is simply zero. This is called a fixed constraint boundary. And basically it means that the boundary isn't moving in any way. We could specify what the displacement is, so we could cause it to move, and keep in mind that it could move normal to the boundary or perhaps parallel to the boundary or transverse. A particular kind of displacement boundary condition that comes up a lot is where the displacement normal to the boundary is equal to zero. And this is called a roller boundary. Because it behaves as if the boundary was constrained by rollers or like a ball bearing. So basically, if this is the block we're interested in and we have a roller bearing right along this boundary, it's as if there are rollers right here. The boundary could move in this direction, but it could not move normal to the boundary. So that's what that means. And we could also specify what the velocity was, how the displacement changed with time. Stress boundary conditions, if the stress is equal to zero, then this is a free boundary. So if this block was just open here, it didn't have any loads on it, then we would call that a stress-free boundary. We can specify the normal stress. That's another possibility, and we could have a normal stress or a shear stress on the boundary. We could also specify the pressure on a boundary, and in that case the pressure is just acting as a normal stress. Now, one of the things that you'll find when you set up problems like this is that if this is the region, this is your geometry, you have to have it constrained with displacement boundary conditions sufficiently so that the body doesn't move. And so you have to have at least one displacement boundary condition, and sometimes more. So if you have a fixed constraint boundary condition somewhere, then that will be good enough to keep it from moving, at least from translating in a unconstrained way. So one of these fixed constraints, you can also do it with rollers, but if you just put rollers on this boundary here and say on this boundary here, and then you put stress boundary conditions on the top and the bottom, then that can cause problems, because let's say that we had rollers on these sides, a stress boundary condition here, and zero stress here, so we had some load applied. Well, this block would move in response to this load, and it would just keep on moving. It would move in this direction because the rollers would prevent it from moving this way, but it would just it would have some velocity. It would move, and we wouldn't be able to solve the problem. So if we were to put rollers here and rollers on this side as well, then it would be constrained, and then we could solve it. So if you have problems early on when you first try to run the model, then and it doesn't converge, then check and make sure that you have it fully constrained. Okay, so the properties that we need to be able to come up with are the Young's modulus and Poisson's ratio. These are material properties, the density of the material, and so we'll need all of those in any case. And then if we're interested in what happens if the body is loaded by gravity, then we need the volume force or the body force, and this is typically going to be the unit weight of the material. We'll see that there are other possibilities, but for this week, we'll just really be concerned with the volume force being the unit weight of the material. Okay, so we need to be cognizant of the sign convention, and in Comsol, it uses the engineering sign convention. So a positive stress is tension and a negative stress is compression. The three principal stresses that define the stress state, the first, second, and third principal stress, are designated using this convention. So the first principal stress is the stress with the greatest positive value, and it is, as a result, the most tensile stress. The third principal stress is the most compressive, and the strains are similarly. The third principal strain is the most dilational, and the third is the most compressive. Now, when we go to specify boundary conditions, this can be somewhat tricky because you need to get the boundary condition, particularly if it's a stress boundary, to act in the right direction. So if you specify the stress, the boundary stress, using global coordinates, then plus y is equal to up, and plus x is left to right in the coordinate direction. So if you specify, and so actually then the boundary stress is specified using these coordinates. So if it's positive and it's perpendicular to the y direction, then it would be acting upwards. Okay, so we can specify the boundary stresses using a global coordinate, but it's also possible to specify the boundary stress using what's called the boundary system. This is just a simple switch on the software. You can change it, and if you use the boundary system, then the convention is that the vector pointing outward, normal to the boundary, is positive. And if we specify it as pressure, so this would be a positive normal stress. If we specify it as pressure, and that's something that can be selected in the boundary as a boundary condition, and it's a boundary system, then it's acting inward from the boundary. Okay, so you can go back and refer to these if it would be helpful. But one thing that I think just to keep in mind, this is kind of confusing. You can have these different ways to specify boundary stresses, and I think the upshot of this is that as you're getting used to this, you just really need to set the boundary condition up and then run the model and just check and verify that it's acting in the right direction. Okay, so here's a simple example. We're going to take a block, put a load on it in the negative y direction. We'll use that magnitude of load, 10 to the 6th pascals, 1 megapascal. We'll fix the bottom of it, and we'll use these properties. That should be a row right there. Okay, so when we do that, we'll get a stress distribution that looks like this. So we're pushing down on it, and the stress, the red color here, is minus 1 times 10 to the 6th. So that's the stress that we applied here. And we can see most of the block is at that stress. But there are some places that are, and it's negative, so that's compressive. Some places that are a bit higher. And then there are these places here that are quite a bit higher. Or actually, this dark color is a bit lower. a bit more positive, and then this is even higher compression at these corners. So the thing that's going on here is, I mean, this is kind of peculiar because we're just pushing down on this block, and we've got down here a fairly non-uniform distribution of the stresses. And so the reason for that is because of the way the lower boundary condition is acting. So if I allow the block to deform, and this is just an option you have in the display, so I push down on it and I allow it to deform, you can see that the boundary condition has caused it to deform in a non-uniform way. The fixed constraint boundary is preventing the boundary down here from moving at all, but when we push down on it, the sides bulge out here, but they're not allowed to bulge right here at the boundary. And so we've got this progressive bulging out from the bottom corner outward like that. And as a result, as you're pushing down, this material here wants to spread out, but it's stuck to the boundary, and that's what causes this buildup of stresses. So it depends on the problem that we're solving, but this may be a problem, may be a difficulty, because we may want to have a situation where we're interested in creating a certain stress state in here, and that's what we're really focused on. And we don't want to have these stress concentrations here that are a result of the boundary. So one option is to use a roller boundary. What's happening here is we're pushing down and we're getting lateral movement. We're getting lateral movement here, clearly because it's bulging out, but we can't have lateral movement here along the boundary, and that causes these stresses to build up. So one possibility is to replace the bottom boundary with a roller. That'll allow there to be slip here, and that will hopefully reduce the buildup of the stresses. So I would try setting this problem up, and you have the load here and the roller, and give it a try, and you'll see, I believe, that it will have difficulty running. In fact, I would be surprised if it runs. And that's because we have this problem that it's not constrained in the x direction. This thing can move this way. There's nothing that's preventing that, and so that will prevent it from converging. And so the path forward then is to put rollers on the sides and rollers along the bottom. And when you do that, you apply a stress at the top, and this is what you get. You apply 10 to the 6th pascals at the top. You have a uniform stress here throughout the whole block equal to 10 to the 6th. If we go over to Comsol and take a look at an example, here's this square domain, and in this case I've applied a load to the top, and I've applied it in the positive y direction, so I'm stretching it. The load now is negative, and I get contraction here from the sides, but I still get these stress concentrations down in the corners. And here's the setup. It's a solid mechanics physics interface, and what I did for this example is to, well, I guess what I did is to just type in the parameters here, and then the boundary condition here is a boundary load, and I put here's where the global coordinate system is used for the type of boundary condition, and it's y 1 times 10 to the 6th. It's positive, so it's acting in that direction. Now I told you about this other type of boundary condition where it could be normal, or where it could be called a boundary system. So if we do that, then what we specify is this is the normal and this is the tangential load. So if that's the case, then the sign convention is positive is the outward normal. But for now, we'll just use this boundary condition. Let's switch it around and try running this. This is the one that we used back in the example in the PowerPoint. And I've got a contour here turned on, and let me disable that. And also, I guess I need to change the plot to the third principal stress, which is what we were looking at. Okay, so there's the plot from the video. And if we change the boundary condition, I've got this set up for rollers on all three sides. And so the lower boundary here is set up as a fixed constraint. So I'm going to just disable that and enable the rollers. And then if I run that, I get this uniform stress. Okay, so this is really going to be the way we want to go if we're interested in doing something in here and seeing how that affects the stresses. It's a good baseline. Okay, so now let's take a look at what happens if we include a body force. And we'll go back to the original setup where we have a fixed constraint here on the bottom. The sides are all free. And instead of having a load applied to the top, we're going to have a body force that basically is accounting for the weight of this block. And we'll have the same material properties. So when we do that, we get a distribution that looks like this. This is now the third principal stress. So this is the maximum compressive stress. And you can see when we have the constraint, we still have this stress concentrated here in the corners, but we've got this bulging outward. The bulging now is got a bit of a different pattern. It's there's no bulging up here at the top because this all is from the load is from the weight of the material. So this is in this deformed view, this is the top of the surface, and so there's no load here. The load increases with depth, and we have this outward bulge. We also just have this subsidence, or this downward displacement from the weight of the material. And what's shown here with these arrows are the stresses. So the magnitude of the stresses is shown by the length of the arrow, and the direction of the stress is shown by the direction of the arrow. So we've got maximum compression vertically, and this arrow here is compression horizontally. We noticed up here, if we were to zoom in here, we would see very little or essentially no horizontal compressive stress, and that's because these sides here are free. They're stress-free, so the lateral stress is negligible here, essentially zero. We have some lateral stress here, though, because of the boundary condition here, because the boundary is fixed. Okay, so these are stresses from the self-weight of the material, and if we change the boundary conditions and do it with rollers, then we have things changing a bit here. The stress now is shown in red, or shown in colors. So this is small stress, and the compressive stress increases with depth. And we can see the stress vectors, or the stress symbol here is also increasing in size, and it's uniform now. Here, each one of these stresses, there is some lateral stress associated with this condition, because as the material loads itself from its own weight, the boundary conditions, the roller boundary conditions, prevent lateral displacement, and that causes the lateral stresses to build up. So when we include body forces, we have the compressive stress increasing with depth because of the weight of the material. When we did this problem before, where we had no body stresses but we had just a surface load, Then we had this case, okay? So a uniform stress. So that's the difference. Stress is changing with depth, whereas if the load is applied at the boundary, we have a uniform stress. So including the body load is straightforward. If we go here in the solid mechanics, we can include it right there, and we'll enable it here. And so when I enable it, I'm also going to turn off the boundary load, which is what I had up here pushing downward. So we'll just disable that. And the body load is the unit weight of the material, which is the density times the acceleration of gravity, and it's acting in a vertically downward direction. So we can run that and we'll get the solution that we just saw. And here's how you turn on those stress symbols. It's called principal stress surface. And where you're going to find that is if you go, let me see. Well, maybe I'm not quite sure. I thought it was right here, but I don't see it now. Oh, I know, up here in stress. So in stress, where this is the plot group, so go to the plot group, and then under more plots, it's principal stress surface right there. And we turn that on, and we see the stress, the symbol that indicates the stress directions. Okay, I think that's all I want to show for that. Let's go back to the PowerPoint, and these are for these examples are just for uniform blocks, but there's an important example that we should look at where the block has a hole in it, and this will cause stresses to be concentrated. Now, in the previous example, we saw stresses concentrated at the corners of the block, depending upon how it was loaded. Those stresses were caused, essentially we could think of that as friction between the block that was deforming and the base plate. But we got rid of that by putting these roller boundaries on there. And now let's take a look at what happens if we have a hole here. And that hole, and then we pull on it, and this hole will concentrate the stresses. So the first example that we'll look at is for a circular hole. So this is an ellipse, but a circle is a special case of an ellipse where the two axes are the same length. So this is the problem. We've got this square block and a circular hole here, same boundary load and same rollers along the boundary. And when we do this, we get a result that looks like this. And what I'm showing here is the first principal stress. We're applying tension here. And so we look at the first principal stress because this is showing the maximum tension. So what you get is now this non-uniform pattern where there's some warm colors here and cold colors here. And so what this is indicating by the warm colors, this is a larger tensile stress. And if we realize that we're pulling on it with 1 e to the 6th, there's 2 e to the 6th, and the max is 2.7 and change times 10 to the 6th. So what's happened is we have a concentration of stresses by about 2.7 times here right in the wall of the hole. And if we look here, this is potentially 0, very small stress. And so what's happened is when we pull on this, think of this maybe as a plate with a hole in it. When we pull on this plate like that, we cause an increase in the tensile stress right here and a decrease right there. And the reason for that is because the tensile stress that we're applying over this length of boundary has to be transmitted through the whole block. And when it's transmitted through this cross section, we can't have any tensile stresses transmitted across this hole. So the tensile stresses that were applied here have to go around the hole. And when they go around the hole, they're simply concentrated right here. And so there's an increase in tensile stress right there. Okay, so that's kind of interesting. Materials tend to fail in tension much more readily than they do in compression. And so here's a mechanism. Just by introducing a hole in the material, we can increase the tensile stresses by a factor of 2.7. This is a particular size, but as it turns out, this is really just in this model, it's a particular size because we had to specify the size in the geometry. But as it turns out, this is really just an effect of the geometry of the hole, and it will happen no matter what size hole we have. So because it's a property of the geometry, if we change the geometry, then we will change this effect somewhat. And so what I want to do is to change the geometry back to the ellipse that we looked at earlier. And I'm going to make it a broad, flat ellipse. So the semi-axis is 0.2 in this direction and 0.02 in this direction. So it's a 10-to-1 aspect ratio. The load is still the same load, 10 to the 6th. And when we do it, and we do this and apply the first principle, or plot the first principle stress, we get this. So at first blush, it looks like there's not much happening. But let's take a look at the scale here. So this is 10 to the 7th. And so there's 1 times 10 to the 7th. Well, this blue color is down here, though. The applied stress is 0.1 times 10 to the 7th, 10 to the 6th. And it looks like a lot of this could be pretty much like 0.1. So there's not much happening that you can see at this scale because the action is right here. Our first tip off that something unusual is happening, though, should be when we look at this scale, because this is 2.2 times 10 to the 7th. And remember last time the maximum stress that we got here was 2.7 times 10 to the 6th. So this maximum value is roughly 10 times greater than what we had for the circular hole. And we can see the pattern of the stresses a little bit better if we change the scale. So this is all of these are the same plot, and I just changed the scale on the plot here, and you can see now that there's something happening here at the tip of this ellipse. There's some bright or some high values right here at the tip, and we have this kind of two lobes of stresses coming off of the tip. And so if we blow up this region right here and we go back to this scale, then we see what's happening. This large tensile stress, 22 times greater than the applied stress, is being applied. It occurs right here at the tip of this elliptical hole. And we can see this pattern of stresses associated with that. So the significance of this is that materials have lots of long thin flaws in them. They're micro cracks, and they're shaped somewhat like this. In fact, in a lot of cases, they're shaped with even a larger aspect ratio than what we have here. So the length in this direction is even much smaller than it is in this direction. And what happens is these micro cracks will concentrate the stresses at their tips, just like the stresses are concentrated here. And so the net effect of this is that these flaws, these micro crack flaws, concentrate the stresses, and when a load is applied to a material, the stresses that are concentrated at the tips of these flaws are that's the place where the material will fail first. So the material fails here first, and their bonds are broken, and this hole propagates out like this. And indeed, this is the way that fractures are represented in materials, and the propagation of fractures is simulated by calculating the stresses and evaluating whether the stresses have exceeded a failure criterion. And if they have, then you say that the failure occurs right here, and the bonds break, and this fracture propagates out. We won't do that. That's a more of an advanced analysis, but that is how fracture propagation is analyzed. Okay, so we can combine these two different concepts, the body force with a circular hole, and we'll set it up like this. And what I have in mind here is a material that's loaded by gravity that has a hole put in it, and we'll look at the concentration of the stresses around it. And one thing you might use as a visualization of this really idealized case is if you had a block of rock and you wanted to put a tunnel through it. Rock is often, well, rock will definitely be always loaded by gravity, and that'll be a significant factor in many cases. It may also be loaded by tectonic stresses, but it'll always be loaded by gravity. And so if we had a case where there was I guess in this case it's a large block of rock that's freestanding. So yeah, I guess it's a block of rock without any constraints on the sides, and we put a tunnel through it. What would happen in that case? So let's take a look. Here are the results, and actually I'm pretty sure, looking at this, I'm pretty sure that it's that this case that I'm showing on the next page has roller boundaries rather than open as I'm showing here. Okay, so we apply the body force, and here's the first principle stress. So we can see up here at the surface, this is this red color, and actually I've included a contour right here of zero stress. So this is at the ground surface, and you can see this red color comes down here, and the hole has zero stress applied to it. And we can see that the first principle stress is essentially zero around the hole. That contour right there is the zero contour. Okay, so that's not too surprising because that's the stress that we apply to it. The principal stress in this case, this first principal stress will be perpendicular to the boundary, so it'll be acting in that direction. But now let's look at the third principal stress. This will be the maximum compression, and we see over here on the side that it's increasing with depth. That's what we expect, but we see here around the hole that we've got a pattern of the principal stresses that apparently is resulting from the presence of the hole. And what the pattern is showing us is that right here, this blue color, this is high compressive stress. So the blue color, actually that blue, that looks like the highest blue in the whole region. So that compressive stress is even higher than the compressive stress that you have down here at the bottom of the model. And right here, this color here is essentially it's zero. So what we have is that the body force is causing the compressive stress to increase downward, but the stress is being concentrated right here at the walls, And it's really the same kind of argument that we had for stress concentration previously, that the lines of force have to go around this region and they get concentrated here in the walls, and so we've got large compression right here in the walls. And so if this was a tunnel, for example, then this large compression could end up causing some problems. The stresses can become concentrated here in the walls and cause deformation. And here we have some unloading of stresses in the roof and the ceiling. So to set up that model, the last one, we go here to the geometry, and I've got an ellipse in here that I'll enable. And let's see, if I do that, then the ellipse is set up so that the semi-axes are the same. And if I build that, then there's the ellipse. It's of course a circle at this point, and then I use the difference function to, let me see, I'm going to turn that on, to make it a whole. So I take this block and I subtract from it that block, and I get a whole. Okay, so there's the whole, and if I wanted to make this a long thin ellipse, then I would just change the semi-axis like that. So there's the circle, and the problem is set up really the same as it was before with the body force, and so we run it and we get the image that we just saw from the PowerPoint.